Okay, we've looked a lot at indefinite integrals with our u sub. Well, we can do a u sub when we have a definite integral also. Ah, cool, right? The same thing holds true. Remember we talked previously that anytime you do a u sub, everything has to be in terms of u. That includes the bounds. Everything has to be in terms of u. That includes the bounds. And I am going to be a stickler on that. I am going to ride you. Because some people teach it where you don't necessarily have to change the bounds. You just put it in later. I'm not even going to go there. Because I know where you're going. Calc 1 is preparatory to get further into the calculus series. That's how I'm teaching it. That's how we've been talking about it in class. So I'm not even going to go with this whole, sub back in, whatever. No, because I know where you're going and it's going to make an impact. All right? So make sure that anytime you do a u sub, everything changes, including the bounds. Okay, so let's try this one on. Here's example 4a. I'm integrating from 0 to 2 of dx over x plus 3 cubed. All right? So what's my inside function? The x plus 3, right? So u here is x plus 3. du, the derivative of that, is just going to be dx. So here I have my bounds over here. I'm going to make this u, and I'm going to bring it to the top with that negative 3. And du, right? The dx becomes du. Now here's the key. These bounds are in terms of x because that is my differential. In order to change and have new bounds that are in terms of u, I have to sub those in. So you're going to say at x equals 2, u is equal to 2 plus 3. I am subbing this 2 in for this x to figure out what u equals. Do you see that? If I plug it in for that 2, my u, when x was 2, u is equal to 5, and that is my bound. Right? So where x is 2, u is now 5. So you need to write on your paper. And I'm okay if you just writing at x is equal to 0, u is equal to 3. Because I'm plugging in 0 plus 3 is 3. You don't have to show me this substitution. You can do that in your head. But I want to see this somewhere so I know that you are on board, that we're all good with it. Once you make the conversion to u, you never have to go back. You never have to go back. Now we take the antiderivative. I probably should have gone to the other page, huh? Oh well. So I'm going to add 1 to both sides here. And I end up with a u here to the negative 2, bringing that in front as a negative 1/2. And that's going to go from 3 to 5. I'm going to leave the negative 1/2 in front because I've got enough fractions to deal with. So I've got 1 over 5 squared minus 1 over 3 squared. I'm going to bring this up here just because I didn't do a good job with my spatial here. So I've got a negative 1/2. And then I've got 1/25 minus 1/9. Oof. That's just going to be a pain, isn't it? Because nothing goes into both of those. So what's going to be my common denominator? What's 9 times 25? I don't know. Figure it out. 5, 4, 18, 19, 20, 21, 22. 225. Check my math. Did I do that right? And that's going to end up being 9 minus 25. Right? Because 9 times this numerator, 25 times that numerator. Okay, yep, 225. I'm pretty confident in that. So now I've got a negative 1/2 times 9 minus 25 is what? A negative 16 over 225. So a negative times a negative is a positive, and 2 goes into 16 8 times. So honestly, that wasn't that bad. Is equal to 8 over 225 is our final answer. All right. The takeaway here is when you change your bounds for a definite integral, you never go back to x. Once you make the change to u, your bounds change to u and you just move forward. The only time you ever have to plug the x back in is if it's an indefinite integral. Squeeze this up here, like this problem up here, right? I didn't have any bounds. I'm not sure what my constant is, so you have to go back in terms of x. When you have a definite integral, you just move forward and then you come up with your answer. Okay, let's do some more. Here we have, I'm going to make this a little bit bigger. Example 4b. And what do we have here? Integrating from -1 to 2 of x squared over x cubed plus 2 cubed dx. Nice. And are you noticing patterns yet? This is the weird crazy. It's in the denominator. It's on the inside of a function. And I have an x cubed. And this is an x squared. Cool, right? That's a good tip-off that we're going to be doing a u sub. Okay, so let's do it right now. U here is equal to x cubed plus 2. So du is going to be a 3x squared dx. I only have an x squared, so I'm going to bring that 1/3 in front. When you divide both sides, it gives me that 1/3 of x squared dx. All right, so I've got 1/3. I don't know my bounds yet, but now I end up with, this is just a 1 over u cubed, so I'm going to write it as u to the -3 du. When you go variable u, bounds are u. At x is equal to 2, then you plug that 2 in. I'm going to take this 2, plug it in up here. 2 cubed is 8 plus 2, so u is 10. At x equals -1, I'm going to take my -1, plug it in. -1 cubed is -1 plus 2 is a +1. So my bounds are going to go from 1 to 10. Also, 98% of success in mathematics is what? That's right, organization. So for me, I like to keep it organized. 2 is on top, so that's the first one I write. So I know that these are my bounds. 1's on the bottom, 10's on the top. 1's on the bottom, 10's on the top. So that I make sure that I'm lining them up correctly. All right? Okay. With a definite integral, you never, ever, ever go back to x. Change the bounds and never go back to x on a definite integral. That's a big deal. Never go back to x with a definite integral. Okay, I'm quit beating that drum here. If I add 1 to this, I end up here with u to the -2, bringing that -1 in half, and then don't forget I've got this 1/3. And I'm going to go from 1 to 10 on that. So I'm going to keep this -1/6 out front, and I'm going to have 1 over 10 squared minus 1 over 1 squared. So we've got a -1/6 of 1 over 100 minus 1. So I'm going to make that a 100 over 100. So -1/6 times a -99 over 100. We can simplify that a little bit, can't we? Divided by 3 is a 2. Divided by 3 is a 33. A negative times a negative is a positive. So we're ending up here with 33 over 200. Yes, I do expect you to be able to do that kind of math because it's not hard. All right. Moral of the story, definite integrals. Keep moving forward. Nope, there's not enough room on there. I've got one more example to go through here. One more, because I want you to do a little bit of, guess what? Trig, baby. From 0 to pi over 2 of sine to the 4th x cosine x dx. All right? What's the crazy part? Sine, right? Because that's to this big exponent. So we know if the exponent is between the trig and the angle measurement, then that is an exponent to the whole thing. So u is going to be sine of x. That means du is what? Cosine x dx. Well, we just happen to have a nice little du that we can sub out. Isn't that handy? Well, it sure is. At x is equal to pi over 2, plugging in pi over 2 to sine, what do you get? 1. Good. We should know that by now, right? If x is equal to 0, when I take the sine of 0, what do you get? 0. Look how nice this is turning out to be. I'm now integrating from 0 to 1 of u to the 4th du. We took something that was crazy trig and put it into a super easy, simple, one-term integration. That is so nice. U to the 5th and a 1/5 in front. And I'm taking that from 0 to 1. So I've got 1/5 times 1 to the 5th minus 1/5 times 0. So 1 to the 5th is 1. 1/5 minus 0 is 1/5. Cool, right? Yeah, it's not bad at all. It's good. So the more you practice this, the better you're going to get at it. And this is a big deal. So make sure you are practicing. When you think you've practiced enough, you could probably use another 10. Practice, and then practice some more. You've got this. Good. Good job, guys. Go practice.